So before we get to the space math, we're going to do a short proof that proves that the polar equation of an ellipse with directrix x equals negative d can be written in the form r equals a times 1 minus e squared over 1 minus e cosine theta. This proof is going to allow us to do some other math problems a lot easier later on. First of all, we need to identify the theorems that will be needed. These include a squared equals e squared d squared over 1 minus e squared squared, which from that we can get a equals ed over 1 minus e squared. These formulas come from the proof of the formula of an ellipse. A is half of the length of the major axis, d is the directrix, and e is the eccentricity. Keep these in mind because they're going to come in handy in our next steps. Just as a reminder, the regular polar equation of an ellipse is r equals ed over 1 minus e cosine theta. The equation given to us in the problem is marked with the yellow starting point arrow. We're actually going to do this proof a little bit backwards and take that equation and make it equal the regular polar equation of an ellipse. It's a little bit easier to do the proof this way. Next, using the theorem that we talked about earlier in the video, we're going to substitute for a. This gives us r equals 1 minus e squared over 1 minus e cosine theta times ed over 1 minus e squared. Now, as you can see, the 1 minus e squared term cancels out quite beautifully from the top and the bottom. And voila! We have our answer. We have in fact proven that the regular polar equation of an ellipse is equal to ed over 1 minus e cosine theta. And really, in one step.
Find a polar equation for the orbit of the Earth around the Sun, we use the equation r equals a times 1 minus e squared over 1 minus e cosine theta. In this equation, e is the eccentricity, which is given to be 0.97, and a is the radius of the ellipse. Now we know that the length of the ellipse's major axis is 36.18 AU. And the length of its major axis is the diameter of the ellipse. So in order to get the radius, we divide this number by 2 to get a equals 18.09 AU. When we plug the values of e and a into the equation of an ellipse, we get that r equals 18.09 AU times 1 minus 0.97 squared all over 1 minus 0.97 cosine theta. When we simplify the top of this equation, we get that r equals 1.069 AU over 1 minus 0.97 cosine theta. Since we don't want to have a decimal on the bottom of the fraction, we multiply the equation by 100, and we get r equals 106.912 AU over 100 minus 97 cosine theta, and this is our equation of the rotation of the Earth around the Sun. The aphelion distance is the position of a planet in its orbit when it is the farthest distance from the Sun. So to find when the Earth is the farthest away from the Sun, we will use the equation to find aphelion distance, which is a times 1 plus e. We previously found out that a equals 18.09 AU, and it was given that the eccentricity, or e, is 0.97. When we plug these values into the equation, we get 18.09 AU times 1 plus 0.97, which simplifies into 35.638 AU, so we know that the farthest distance the Earth will be from the Sun is 35.638 AU.